All right, folks. And so in the last video, I showed you guys how to make that systems diagram. Here I want to show you how I would approach going through and understanding the math behind one of the subsystems of your project. And so I'm going to continue working with that FTC robot. Here I'm going to look at the actual arm that moves up and down. And so what I've done right off the bat, I've gotten some information about the input to that arm that moves up and down. It's using a Torquedo motor from Tetrix that has a no load speed of 100 RPM and a stall torque of 700 ounce-inches. And so I've just drawn my skeleton diagram. It's got a gear here that's anchored to the frame, another gear here that's anchored to the frame. I've got a gear train, in fact, between these two. I'm just going to represent that as a gear and delve into this gear train in a second. And then this is what's considered it's pretty standard 4-bar linkage mechanism. And so this thing can move up and down relative to this pivot point, and these parallel bars keep this segment perpendicular to the ground. So a nifty type of mechanism for being able to lift something up and down. And so one way you can think about this is sort of trying to figure out what kind of physics question your subsystem is trying to answer. And so here I've got my input. The ultimate output of this subsystem is being able to lift up some type of mass, my load mass. So this particular robot is supposed to grab a block and move it up and down and deposit it in different parts of a shipping container. And so my question, if I'm using this motor that supplies 700 ounce-inches of torque, here I've got some kind of gear train, I've got a mechanism here, I've measured the length of this arm here. My question is, how heavy of a load can I lift with this arm mechanism? So that's essentially what I'm trying to answer with the physics for this subsystem. So first I'm working my way from my input here, my output. The result of this subsystem is the object being lifted. And so in my block diagram, this is just represented by a couple blocks. The input is the motor, the output is this load being lifted up and down. I think that's labeled as the z-axis on my systems diagram. So let's kind of start at our input. Here if I'm looking at the mathematical analysis of my input, my Torquedo motor, if I have a no load speed of 100 RPM and a stall torque of 700 ounce-inches, I can figure out the max, the rotational speed associated with the max power, which we know is just 1/2 the no load speed, which is 50 RPM. So that's what I would use if I'm operating this motor at max power, and same thing for the torque at max power. So this is the analysis we did on Tuesday. There's a set of notes posted on Google Classroom. And once again, I know the torque at max power is half the stall torque, which is 350 ounce-inches. I went ahead and punched that into Google, and that is the equivalent of 2.47 Newton meters. So we'll stick with SI units for my calculations. All right, so that tells me how much torque this motor is providing to this gear. Here I've got a gear train with an input gear and an output gear. Let me zoom in here to the gear train, because it's actually a little bit more complicated what I have implemented. It's not just 2 gears, it's a couple compound gears. And the way this gear train's set up is there's a little gear connected to a big gear, connected to a little gear, connected to a big gear. And so this is my driver, and this is my driven gear. And so the number of teeth for this little gear is 40. The big gear is 120. The number of teeth for this little gear is 40, and this is just another 120 tooth big gear. So I can figure out the gear ratio. So I'm going to go ahead and label that. Let me underline that so I know I'm talking about my gear train. All right, so if I'm calculating my gear ratio, the ratio between these first two pairs of gears, this is the output, this is the input, so it's output over input is 120 over 40 times the next gear pair, which is just the same thing with this compound gear, 120 divided by 40. Well, I don't want to multiply that out, but I know 4 goes into 12 3 times. So that's 3 times 3 is 9. And I've got a force multiplier of 9. So I know if my maximum torque that I'm applying to the input gear is 2.47 Newton meters, I know that my output gear, since it's a bigger gear, is going to have more torque. I know that, let's say my torque of, I'll call it G for gear, is equal to 9 times 2.47. But I can plug that in, figure out what that is. Or if you don't have actual values for these different numbers, let's just call that, let's see, M times torque max power. So that's my equation for the torque at the output gear. And so that's the torque being supplied at this joint here. Now I'm trying to lift a weight, and that is extended along a lever arm here. So I've essentially got a wheel and axle. You can almost disregard in terms of the physics, all this other stuff going on here. So if I'm supplying approximately 18, so that's 9 times 2 is 18, plus half of 9 is 4.5. So that's about 22.5 Newton meters. How much weight can I lift up at a distance of 288 millimeters? Well, that's another simple torque problem. So here I've got a torque here. Yeah. Here I've got a weight out here. So based on this lever arm, we can figure out how much torque is required to lift this object with mass m. So this is going to be my radius. This is going to be the force due to gravity pulling on my load. Is going to be, lost my mic. Is going to be the tangential force. And so the torque that this force generates on this load, let's call this, let me move down here and call this load analysis. So we know in general torque is equal to force times a distance. So in this case, the torque generated by the object that I'm trying to hold, that's just going to be the torque that's the output of my gear train times the force, which is the force due to gravity times the gravitational acceleration times d. Oops, sorry. Let me rewrite that. Applying this equation, the torque generated by my gear train is, again, like I said, the force due to gravity, which is m, the mass of the object, times g, times, in this case, the distance here, which I believe I've labeled in my drawing L. And that's just another equation I can use to figure out the mass of the object that I can lift. And so the mass of this object, just dividing by g times L, is the torque generated by my gear divided by the gravitational acceleration times the length of my arm. And I can, of course, plug in numbers here. We figured out, at max power, our torque is 22.5 Newton meters divided by 9.8 meters per second squared times 0. Let's see, what do I got up here? Yeah, I got the length here in millimeters. So converting that to meters is 0.288 meters. So that'll give me kilograms squared per kilograms meters per second squared, which is mass. Let me grab a calculator and punch that in a calculator. All right, so let's see, 22.5 divided by 9.8 divided by 0.288. So this tells me I can lift up about 8 kilograms of mass. So about 4 pounds, which is good, because that should allow me to lift any of the objects in the robotics competition. And so right there, is a basic physics analysis using some of the math we've talked about. So we got force due to gravity, we've got gears, we've got motors, we've got this simple machine here, this wheel and axle, this torque. That's one way we can think about analyzing this. If you wanted to, like if you've got some type of mechanism that moves, you can also look at the mobility analysis. And so I might have another section here in my analysis for mobility. And so here I might calculate like the number of links in my design. So I've got ground link, gear, 2, 3, 4, 5 links in this design. If I look at the number of lower pairs, I got 1, 2, 3, 4, 5, 6 lower pairs. And I've got the higher pair contact point between the gears. So H is equal to 1. And so we know our degree of freedom equation is equal to 3 n minus 1 minus 2L minus H. So n minus 1 is 4 times 3 is 12 minus 2 times. Man, I can't count. 1, 2, 3, 4, 5 lower pairs. So that'll give me 5 minus 1. Okay, then minus 2 times 5 is 10, minus 1 equals 1 degree of freedom. So that could be part of your analysis as well. So one way creating a mathematical model for a mechanism is looking at the mobility equation. So it doesn't strictly have to be force equations like this. But if you have components like gears, we can figure out what are the operational parameters at max power. Motors. If you have mechanisms like gears or sprockets, we can do a gear train analysis and figure out what the gear multiplier is. If we're trying to lift weights, we can do simple force analysis, looking at like the weight due to gravity and normal force and applied force and that kind of thing. And so the free body diagram could be a type of mathematical analysis. The skeleton diagram could be a type of the mathematical analysis. And the mobility equation stuff is something you can include as well. So just a quick example using the system I talked about in the last video. So you're welcome to go through something similar for your project or do something different.